everyone, Sherry Ann here, and welcome back to my chemistry hub. And today we'll be doing a CAPE Unit 2 past paper question, chemistry past paper question, of course. And yes, so let's go. So it reads, describe how each of the following components of a mass spectrometer is used in the analysis of an organic compound. Part 1, you have an electron beam. Part 2, magnetic field. Part 3, a recorder, right? And before we get into the question, let's just do a run through of how a mass spectrometer works. We have our citation there where we got this question from, this diagram rather from. So let's get into it. So first, your sample is vaporized, as you see right here. The sample is vaporized and then it's injected into an ionization chamber, which is this thing right here, ionization chamber, right? In the chamber, you have a filament. Let's see. So you have a filament, and the filament is electrically heated. And when it is heated, it gives off electrons. Now, at the opposite end of the filament, you have a positive electrode, right? And the thing is, when the filament gives off these electrons and your positive electrodes, opposite attract, it will want to move towards this positive electrode because, as I said, opposite attracts, right? Everybody knows that. Now, when it moves towards the positive electrode, it bombards or collides with the molecules of your sample and essentially knocks off one of the electrons on the molecule to form fragment ions. So let me see if I can show you what's happening. So this is the molecule of your sample. So you have electron bombarding and colliding with it, right? So when it bombards and collides with it, it breaks it apart to form fragment ions. So you have something looking like this. And this occurs in the ionization chamber. Ionization, first step of mass spectrometry. Ionization. Now, the next step is acceleration. How does acceleration occur? At this end, what you can see here, you have the repeller electrode. This is another positive electrode. So when the electrons collide with the molecules of your sample, breaking it apart to form ions, positive ions that is, the positive electrode, like repel, pushes these cations through these slits that you see here, right? And focus them into like an ion beam. Now they're accelerated so that they will all have the same kinetic energy. So that's the second step. So I'll just write it out. So the first step, ionization. Second step, acceleration. Right? Then, as you write here, these are electromagnets. The ion beam that I was referring to passes through electromagnets. So it passes through a magnetic field. Now, what happens there when it passes through this magnetic field? You have deflection occurring, which is the third step of this process, right? And now the extent by which the deflection occurs depends on two things. The extent by which the deflection occurs depends on two things: the mass of the ion, and also the charge. So the charge of the ion. In terms of the mass, the lighter ions, the ones with the lighter mass, deflect more than the heavier ones. And in terms of the charge, the ions with the +2 charge deflects more than one with the +1 charge. So for instance, you have a ion with, let us say, a mass of 28. Now it's lighter. You have a mass of 31, that's heavier. This will deflect more than this, right? So the lighter one will deflect more than the heavier one. One with a +2 charge will deflect more than one with a +1 charge. Now these two factors combine to give you the mass charge ratio. The mass the mass charge ratio, and it's written something like this: mass charge ratio, right? And so after deflection occurs, let me kind of clear up some space here. After deflection occurs, the fourth step is detection. So the ion stream that I was referring to, it reaches the detector. It hits it, and then a flow of electrons is detected. So when it hits the detector, it results in a flow of electrons. And then this is detected as an electric current. It's amplified and then recorded. So it hits the detector, results in a flow of electrons. Flow of electrons detected as an electric current, amplified, recorded. So those are your steps for the detection stage. And then when it's recorded, you obtain a spectrum. I'm not sure if I can see what's on the screen here, but something looking like this, but we'll see it as we proceed and go into the question. So that's basically the steps of mass spectrometry: ionization, acceleration, deflection, and detection. Let's go back to the question. It says, describe how each of the following components of mass spectrometer is used in the analysis. So for the electron beam, that's when the filament is electrically heated and produces the electrons, rather. So filament heated, producing the electron. This electron beam collides with the molecules. Remember that part? Collides with the molecule of your sample to produce fragment ions. And this, and of course, this is the first step of the process, is ionization. What about the magnetic field? Let's write this down here. Magnetic field. It's supposed to be a D there. Magnetic field. So we all know that the magnetic field aids in deflection. Field aids in deflection, right? That's the third step of the process. We also discussed that as well. And the recorder produces a spectrum. Recorder produces a spectrum, or acts as an output, produces a spectrum of the vaporized sample. So this is where you have your output to know how to characterize your sample or what's in your sample that you just vaporized. So essentially, that's how each aids in the analysis process. Right? So the next question, it says, explain the importance of the M+1 peak in mass spectra, in a mass spectrum. So the M+1 peak is a peak with a mass 1 unit heavier than the molecular ion peak. Now the molecular ion peak represents the RMM, that's the relative molecular mass of the molecule that you're analyzing, of the sample that you're analyzing. So it is the M+1 peak, a peak 1 with mass 1 unit heavier than the molecular ion peak. And what this M plus 1 peak tells us is that there may be present in your sample carbon-13 or hydrogen-2 isotopes in some of the molecules. So it represents your isotopic peaks within your sample. Right? So that's the M plus 1 peak. So where should I write this? Right. M plus 1 peak represents the isotopes that may be present in some of your molecules. Okay, so moving on to part C, it says figure 3 shows the mass spectrum of a sweet-smelling organic compound. Sweet-smelling organic compound. So that's a clue. Sweet-smelling organic compound, that should tell you that this may be an ester, right? Should just bear that in mind. The question says, deduce the following. What's the mass charge ratio of the molecular ion peak? Mass charge ratio of the molecular ion peak. So, as I said before, the molecular ion peak represents the relative molecular mass of the molecule. And the molecular ion peak is usually found among the peaks of the greatest mass. The greatest mass in the spectrum, but not necessarily the peak with the highest mass, since you may have isotopes present in your sample. So remember, so if your molecular ion peak is usually one with the greatest mass, but remember you can have your M plus 1 peak present, which would be one mass unit heavier than your molecular ion peak. That what we were discussing before. So in this case, your molecular ion peak, the mass charge ratio would be 88. So the mass charge ratio is 88. Then it says the mass charge ratio of the base peak. Now the base peak is the fragment, the most stable fragment. Remember in ionization, when the electrons hit the molecules of your sample, it breaks apart into fragment ions. Now the most stable fragment ion is known as your base peak. Now the base peak, if it's the most stable, it would be the one with the highest quantity, the highest relative abundance. So your base peak in this case would have a mass charge ratio of 43. Hope we're seeing that. So the formulae of the ion fragments of mass charge ratio 15, 29, and 43. So that's 15, 29, and 43. Yes, the base peak. So they want the formulae of 15. Usually, when you see a mass spectrum, 15 usually represents a methyl ion. So 1 carbon, that's the of our RMM12, and 3 hydrogens give you a mass charge of 15, right? So that's usually a methyl fragment. So when the electrons hit your molecules, it breaks apart and you have methyl fragments being present in your spectrum. So what about 29? So 29 is usually an ethyl fragment. If you count it, it would be 12 times 2, 1, 2, 3, 4, 5. 1 times 5. You all know this is the RAM of carbon. This is the RAM of hydrogen, 12 and 1. That's what we're using to calculate the mass charge ratio. So this will be 24 plus 5. You get 29. So that's where you have your ethyl fragments being present. represented on your spectrum. So this would be an ethyl fragment. Now your base peak, which is 43, right? Remember in the beginning that they stated that it's a sweet smelling carbon compound, and I stated that that's a clue to point you in the direction of an ester, right? Now the functional group are, yes, the functional group that exists in an ester, something like this. You have R can be a different group. So that would be your functional group for an ester. So bearing in mind, this may be like a trial and error thing to obtain what would equal to 43 in terms of when you add all the RMMs of the atoms within the fragments, right? So let's do a trial and error. Say I combine ethyl fragment, remember we're talking about that? Ethyl fragment, ethyl with, so suppose your molecule breaks apart. So we say maybe this could be the base peak, maybe. But let's add it up and see. So 3 times 12, that would be 36, right? Plus 16, plus how much hydrogen? 1, 2, 3, 4, 5. 5. This will be more than 43. So you know that this would not be the fragment that is represented by the base peak 43, right? So let's try next one. So for instance, it looks like this. And that would be what? 12 times 2, because 2 carbon, 16 times 1. It's 1 oxygen, that's the RAM that we're adding up. And 1, 2, 3. 1 times 3. So at 24 plus 16 plus 3. That gives you 43. So this would be the formula of your base peak. The fragment that is represented by 43 on your spectrum. This right here, right? So basically, you have to do like a trial and error thing sometimes. And the thing is, they gave you a clue that it's a sweet smelling organic compound. So that kind of allows you to think in the direction. So, sweet smelling. Oh, esters. Just bear that in mind when going forward. Look out for the clues or the hints that they give to you. Yes. So let's try that. The last question says the structural formula of compound X. Structural formula of compound X. So I have a methyl fragment present. Right? I have ethyl fragments present based on what we just did. I also have this fragment present. Right? So based on that now, and if we know that an ester has a functional group like this, then more than likely when you put other fragments together or when you trying to deduce the structure, it will look something like this. So I have this part, join that part, and then you can have the ethyl fragment over here. Let's put in my H's there. Gamma H is there. So more than likely, you will have, this would be the structure of your compound, of compound X. So we have the ethyl fragment, the base peak, the fragment that represents the base peak, and also the the methyl fragment, the fragment that represents the base peak would be that which would be the most stable fragment, and we also have the ethyl fragment. So the methyl fragment. So when your sample goes into the ionization chamber, the electron hits it here, and it breaks apart, giving you the ethyl fragment, the methyl fragment. Sorry about that. And then so another time, it breaks here, right? Breaks here, giving it a fragment. So it comes again and it knocks right there, breaks, giving you the fragment that represents the base peak, which is this. And then at another time, some other molecule breaks here. It hits here and breaks and give you that fragment ion, which is the ethyl fragment, which is this right here. I hope you're seeing what I'm seeing. So basically, it's like a puzzle piece. You're trying to put together the different fragments to deduce what your structural formula is, or what is the compound that you're analyzing. So yes, that's the final question. Yeah, that's the final question. So thank you for joining us today. I really do hope you learned something about mass spectrometer and the whole process of analyzing a spectrum and deducing the structural formula of your compound. So join us again and next time. Thank you and bye.